Um, I'm actually really happy to be like the first technical talk because it means I get to relax for the rest of the conference. It also means you guys are probably not skipping out on the talks yet, so you're all here. It's a full room, so that's good. Welcome to RubyConf, guys. I'm really excited to be in Miami. I want to start my talk with a question, and that question is, are Rubyists good at testing because they have good tools, or do Rubyists have good tools because they're good at testing? It seems to me like this one is sort of the wrong question to ask because there's nothing, to me there's nothing innate about Rubyists that make us good at testing. First of all, a lot of Rubyists are also Java programmers, Python programmers, Go programmers, and when we're programming in Go, we're not all of a sudden bad testers. And when we switch back to Ruby, we don't become magically good testers again. Clearly, there's something about the tools that we have as Rubyists that make it efficient for us to be good at testing. You can also look at sort of the ways we've advanced our civilization as humans. Sort of the way we've been able to survive as humans over the centuries and millennia has been through the advancements of technology and tooling. Humans are actually kind of weak creatures. We're not very good at physical dominance. So we've always used our ability to advance technology as our survival mechanism. And I think the advancement of tooling has always sort of been central to the advancement of technology, which has sort of given us better tools, and then we've finally gotten mastery over our crafts. So clearly tools are important. And I think just because tools are important, we should talk about what tools are available to us and figure out how we can use the tools that we have and figure out how we can make better tools. So in the Ruby community, we do have good tools available to us, and there's plenty to talk about. But sometimes we don't really have such great tools, and I want to focus this talk, even though there's a lot of great things to say, I want to focus the talk on the not so good tools that are available to us and the things that we need to improve. So there are a couple of goals in this talk. The first one is to introduce a different set of tools that you might not be aware of. Let's look at other languages, see what other languages provide to developers as tools. Java, C#, Go. After we look at different tools, we can figure out sort of what tools we are missing from our languages and sort of reflect on that and figure out why we're missing those tools. Are there any problems with the fact that we don't have those tools, and should we be improving ourselves? And the third one is, I kind of want this talk to be hopefully an inspiration to you guys to actually go out there, find a problem that hasn't been solved yet, and write a tool for our community, write something that can make us better. Become a garbage collector, as Matt said earlier. So I'm going to be naming a bunch of different tools, and I'm going to be glossing over a lot of different things in this talk. And I didn't have time to actually give URLs to everything, and you probably wouldn't be able to read them, because usually some of them are long. So if you Google just the tool name and the language, you should be able to find most of the things I'm referencing in the talk. If you don't, come and find me. I'll gladly point you in the right direction. So let's jump into the kinds of tools that are available to developers. There's tons of kinds of tools, and I'm not going to be able to cover everything, and this isn't even a complete list. But there are tool types like deployment operation tools, documentation tools, testing tools, visualization tools, debugging, linting, static analysis tools. I'm going to focus on sort of the bottom half of this, starting from visualization down. We pretty much have deployment and operations down pat. We are very good at this in the Ruby community. We have pretty good documentation tools. We have very good testing tools. We're sort of the kings of testing, as it were. Visualization, debugging, linting, and static analysis, I think, are areas where we have a lot of room to grow and improve. So I'm going to talk about those 4 areas. So let's jump into visualization. I think that some of the most important tools that are out there are visualization tools. Visualization tools kind of encompass debugging, refactoring tools, general actual visualization tools that you can like see how your code works and stuff like that. Profiling tools, I think, are also visualization. So there's a lot. It's a kind of a broad spectrum, but anything that lets you see what your code does is useful. Visualization tools effectively let you know what your code is doing. So without any visibility into your code, you kind of have no idea what you're doing. Imagine that you have a thread in a sealed box. Is it dead or is it alive? So visibility lets us answer that question, peek into that box and actually see what our code is doing. This is a screenshot of Visual Studio, the latest build of Visual Studio. And this is a new feature that they added called the Diagnostics Hub. And it's sort of this profiling tool that gives you some pretty cool input into sort of very detailed parts of your code, like how long it takes to load things, what the actual CPU utilization is of different components of your code, very granular stuff. You also get FPS for a GUI application. If you have a GUI running, you get FPS showing up, which I think is kind of cool. So you get a lot of visualization stuff from a tool like this. Visual Studio also has a debugger in addition to the profiling stuff. And Visual Studio's debugger has always been pretty good. I'm really excited about the feature on the right there that shows you not only the list of the call graph as a two-dimensional list, but you also get the call graph as this tree of things where you are in your code. And the useful thing about that is you not only see where you are and where you came from, but you also see where that thing that came from was as well. So you see that the item view on click up there also came from activate or called activate instance and then called on navigate from and now is calling on navigated to. And you get this very cool tree of where you are in your code and how that affects other components. And I think that's pretty useful if you're working on very large systems that interact with one another. This is Xcode, and this is Xcode's profiler, and it's not very language specific. It can pretty much run profile any binary. But what I like about this is the user interface view at the top, where you can actually see what user interface portions have been activated. I think that's a pretty cool kind of functionality to have for a UI profiler. This is Visual VM, and this comes standard with the JVM, Oracle's JVM. You can pretty much use this out of the box on any JVM code. And there's nothing really special about this profiler. It gives you the standard stuff that you'd expect, except this one kind of comes with the JVM, so it shows you how integral this is to the actual programming cycle. So visualization is really about discoverability. Knowing what your code is doing is one thing, but being able to kind of find out what you didn't know about your code is also extremely useful, probably even more useful than knowing what you already know about your code. So discoverability is a really important feature of good visualization tools. And if you found Waldo, by the way, has anyone found Waldo? Okay, good. So this is Eclipse, a couple of views that you get from Eclipse. The first one is the implementers kind of view that you get. You get to see what classes implement a specific method in your code. That's kind of useful for seeing, like, I implemented this method, set redraw, who's using it, and if I refactor this method, who will I break? And that's kind of useful, especially if you're doing a lot of refactoring. There's also a call references graph that you get to see, which shows you all things from the other side, all things that are calling a specific method in your code. So if I call this isRunning method, I know that if I have this isRunning method I have defined, I know who's actually using this isRunning method. The cool thing about having statically typed languages is that you not only get the actual, it's not just like a search over your code base for the isRunning string. You're actually finding things that are calling that specific implementation of isRunning. So if you were to search for 2s on your Ruby code, you wouldn't actually get interesting data. But if you were looking for toString on a specific Java class, you would be able to actually find the things that are calling that specific toString method. So that's pretty useful if you're actually refactoring code and moving stuff around. You don't just need to have an IDE to have visualization tools. A lot of the things I showed were part of IDEs. But it's not necessary that you have a full-fledged IDE just to have this visualization stuff. There's nothing specific about IDEs here. And I can prove it because of this tool right here. And this tool is not an IDE by any means. It's the Firebug Web Inspector. If you were fortunate enough to use it when it was like the thing to use a couple years back, you know that this sort of saved your life a billion times. Nowadays, we use stuff like the Chrome Web Inspector and other web inspectors, and they're awesome. And Firebug's still around, and it's awesome too. But the real question is, do you remember what web development was like before Firebug? And if you don't remember, it's probably because you blacked it out, because it was really horrible. And the reason it was so horrible is because you had no visibility into what your code was doing. When Firebug came around, it sort of changed web development. I actually attribute the HTML5 adoption, a lot of the social media adoption, social websites, to the existence of Firebug and better tooling around HTML and JavaScript development. The fact that we were able to iterate so much more quickly with these tools, I think, had a huge impact on how we were able to actually put code out there. So I think it's really important. I think Firebug is a great example of how visualization can actually affect development and how it can be a really powerful tool. So this is the Ember Inspector. It's part of the Chrome Web Inspector. It's sort of this like component that you can add in. And this is similar to a standard web inspector that you would see inside of Chrome, except it adds extra functionality, high-level functionality specific to your application. Like you can see your routes that you've assigned. You can see your Ember data that you've pulled in from your data sources. You can see other application. You can see the view tree and see what things are sort of nested hierarchically. I think it's really useful if you're doing Ember stuff. And having this high-level stuff would be really cool. Having something similar for Rails where you can actually see your client-side stuff would be similarly cool. And finally, I want to talk about one last thing, and that's Smalltalk. So this is a screenshot of Smalltalk, one of the earlier versions of Smalltalk. And Smalltalk is interesting because it was designed as a language that was meant to be inherently visual. It was always meant to be attached to an IDE. The design goal was that you were able to see everything that you were touching, and you would be able to touch stuff and play with it and modify it. The concept of visualizing your development environment was sort of pioneered from Smalltalk. And I think we have a lot to owe to this language and the people who developed it to a lot of the visualization tools that we have today. So yeah, it was an inherently visual language, and I think it worked out pretty well. So where do we stand with visualization in the Ruby community? So we have the standard IDEs. I mean, we have RubyMine. We don't have very many IDEs. We have RubyMine. And RubyMine is your standard run-of-the-mill IDE. It provides you your basic set of visualization. You can see your Rails routes. You can have a basic debugger UI. But we don't get too in depth on visualization tools, and we don't have very many visualization tools when it comes to refactoring, when it comes to seeing what implements what, where your code, how your code is structured. We don't have a lot of that, and there's a lot of room for us to actually improve on that, catch up to other languages. What about profilers? So a couple years back, there was a library called memprof, and it was really awesome. It kind of went away. It doesn't really support Ruby 1.9. If someone wants to resurrect this tool, it's really cool. I would like to see that. In the meantime, we have a tool called perftools.rb. This one can run through your code and generate this GraphViz diagram of how your code is running through everything, including percentage CPU time and stuff like that. So you can see that, for instance, your garbage collector took 12% of your running time. This is a pretty useful tool if you're doing performance, and I think the fact that it generates a graph-is diagram is extremely useful. If you're running JRuby, then you kind of get the advantage of having the JVM, and once you have the JVM, you can use things like Visual VM, and you can use NetBeans to do your visualization. You get all the power of a lot of the power, not all the power, a lot of the power of the profiling tools that are available in NetBeans and other tools. So this is not an endorsement, but if you're using the JVM, you get some of the powers. So that's visualization. I want to jump over now to sort of linting tools and how we can, where we are in that kind of area. So Lint is this tool that was developed in sort of the 70s for the C programming language. And Lint was a tool that was meant to sort of find these common errors in our code bases. It was meant to catch things like divide by zeros, uninitialized variables, and other like very, very common, easy to find bugs. But it also did some basic style checking, like using this kind of tab with your formatting is this sort of direct way, and it looks good. So that's sort of, when we say linting, we're sort of saying, do you have this kind of sort of basic bug checking tool? So where do we stand with Ruby when it comes to linting tools? In the Ruby community, we have 3 tools that are kind of used together in some way. They're called Reek, Flog, and Flay. And they basically detect code smells in your code. The thing that they don't do, and I'll touch on this in a bit, is they don't find semantic errors in your code. They basically just find syntactic kind of weirdnesses. The assumption that these tools make is that pretty code is correct code. So if you have code that looks good, it's really good. If you're using Code Climate, you probably already use these tools because Code Climate kind of uses these under the hood, and you get a grade point average for whether your Reek outputs tells you that your code is good or whatever. The important point here is that these tools are telling you whether your code is ugly, not whether your code is correct. And I wanted to figure out a way to like show this the best way I could, and I decided that I would write a really large Ruby application that looked really nice, but didn't actually do anything. And then I realized that writing a really large Ruby application would take me a really long time, so I wrote a program to write Ruby programs. And I wrote a Ruby program. I generated a Ruby program with 134 classes and passed it through Code Climate, and Code Climate seems to think it's awesome. But I'm just going to pop it up here. This is part of the Ruby code that I wrote. So it doesn't do anything. So yeah, code correct, not necessarily true. By the way, I love Code Climate. I think it's a really awesome tool. I think you guys should probably be using it. The important point here is that you really need to understand what your tools are doing and to realize that Code Climate does not replace testing. So you can't just be like, oh, Code Climate says my code is correct. That's not what it's saying. It's saying your code is maintainable effectively. So you guys should continue testing, which we already do, so non-statement right there. There's a tool called Ruby Lint. It's pretty new, and I haven't really had a chance to check it out. If you're interested in writing a linting tool or helping out with the linting tool, this is a good place to start. I think you just Google ruby-lint, you'll find the project on GitHub. I haven't really looked at, I think I tried to run Ruby Lint against the code base that I just showed, and it kind of crashed, so there's work there to make it better. The point I want to make is that nothing really comes standard in the Ruby community when it comes to linting tools. We don't really have a linting tool that we go to and say, why aren't you using this linting tool? So we could certainly benefit from having one. How do other languages fare when it comes to lint tools? So These are some examples of pretty standard lint tools in other languages. JavaScript has JS Hint. It used to be JS Lint, and that sort of fell out of favor. Python has PyLint, which is widely adopted. Java has FindBugs, which you'll pretty much see everywhere where people are doing linting in Java. C# has fxcop, and I think it has some others as well, but fxcop is pretty standard. All of these are widely used and sort of widely adopted and accepted as the thing that you should be using. Why don't we have something like this in Ruby? We should at least have some kind of sanity checking tool for us to use and sort of define what our good standards are. If we're gonna be having these have these good standards, we should have a tool that sort of verifies that we're meeting them. So I'm going to jump down the rabbit hole here a little bit and talk a little bit about some more technical stuff and talk about static analysis. So static analysis is sort of like a lint++. It's you're doing bug checking, but you're doing much more in-depth bug checking. Static analysis, however, is kind of a huge field. It's a very vague term for a lot of different things. And if you actually Google static analysis or a scholar.google search for static analysis, look for papers on this subject, you'll find that there's over 2.5 million to 2.2 million papers on the subject. That's a lot of papers on a subject. If you kind of average 2 to 3 papers per researcher, you're talking like 500,000 to 1 million researchers with different research topics. So there's a lot of fields of static analysis, and there's a lot of things to talk about on the subject. There's a lot of different types of static analysis. There's defect finding, there's memory checking and fuzz testing, there's extended static checking and model checking, data flow analysis, and symbolic execution. I'm going to cover some of these and sort of gloss over some of these as well. And so let's jump into static analysis. So first I'm going to talk about defect finding. Defect finding is basically like Lint. It sort of has a little less emphasis on syntax, so there's less of the does your code have proper white spacing stuff, and more of the does your code have initialized variables stuff. So because most of the tools that I mentioned before have sort of those capabilities where they can check divide by zeros or whatever you need in those languages, most of those other languages already have those linting tools. So PyLint will do some kind of defect finding. FindBugs in Java is named specifically for the ability to find bugs, so it's kind of a defect finding tool. In Ruby, we have a tool called Brakeman, which is specific to Ruby on Rails, but this is sort of a defect finding tool. And if you haven't heard of it or checked it out, I would suggest looking at this tool. I think it's a pretty good tool. I ran it on a couple of Rails projects and had some pretty good success with it. It basically finds common flaws in Rails code. So it'll look for cross-site scripting, SQL injection, mass assignment issues. This is what a report looks like, and it'll tell you that you have a potential SQL injection in this method. It does some static analysis to find these, using heuristics, it does static analysis to find, oh, you didn't do any sanity checking on this params hash and stuff like that. So it's kind of a useful tool to look at. It does have false positives, but I think even if it did have a couple of false positives in this list, just for that one products controller or SQL injection statement, I think it's worth it. So yeah, it's a useful tool to look at. So this is a paper that was written on static analysis, static detection of security vulnerabilities in scripting languages. I bring this up because it was a pretty cool paper to read through. The interesting part about this paper is they found a way to, using data flow analysis, to actually figure out through code paths where code was being used that wasn't sanity checked coming from user input. And the interesting thing about this is they actually wrote a proof of concept of this tool that they defined in their paper, and they ran it against existing real-world code. They targeted PHP in their talk. But PHP is a dynamic language. It's dynamically typed. It's actually looser typed than Ruby is. So you could very easily take that concept and move it over to Ruby. The really interesting part is that they they actually tested this on sizable code bases. We're talking 38,000 lines of code, 6,000 lines of code, large code bases. And they were able to find on versions of these code bases with existing known bugs, they were able to find all of those bugs with 0 false positives. So they were able to prove that it's a very effective way to actually find bugs. So if you are interested in sort of that defect finding stuff, this is a really interesting paper to read through. It's not that hard to read through. So I would look at it if you want to implement something like this, I would start here. So that was defect finding. Let's talk about fuzz testing. Fuzz testing is interesting to us as sort of web developers because it's very relevant to us. Basically, the idea is that fuzz testers test the fact that when you get user input, you can potentially get invalid or malicious user input. So fuzz testers will throw a bunch of garbage into your application and see what breaks it. Hopefully, nothing breaks it. There's a lot of existing fuzz testing tools out there. For C, Java, JavaScript, Python, there's a lot. You can go Google fuzz tester for JavaScript or whatever, and you'll find lots of tools. There are also lots of papers on the subject, so if you're interested in sort of implementing one, there's a lot of resources out there. This is one of the papers that I found on this subject that I thought was interesting. So Microsoft, internally, they have this tool called Sage, and this tool actually runs across a lot of their code bases that they release to the public. And they implemented this thing called automated white box fuzz testing in Sage. And they were able to find a lot of defects with this methodology of sort of fuzz testing. Typically, you have a hard-coded set of data that you want to pass through. So a login form can do potentially SQL injection. So you'll have this like quote or 1 = 1 string that you always pass through to a login form so that you have a bunch of hard-coded values. But I think what they did here is they had some heuristics to say, oh, maybe if I twiddle this bit based on the code path here, I can actually make something work and make something break. So this is an interesting paper, and they sort of describe how they do fuzz testing at Microsoft. It's interesting, just if you're interested about like how Microsoft does development and how they do static analysis, it's kind of interesting to read anyway. So where do we stand as Rubyists when it comes to fuzz testing? We have a tool called Heckle, which is kind of a little older now. It was written by Ryan Davis and Kevin Clark, Seattle RB stuff. And basically what it does is it finds your if statements, your numbers, your conditions, and everything, and it just twiddles the bits, basically. It just turns that if into an unless. It turns the greater than into like a less than. It turns a number into like some other number that wasn't. And it tries to see if your tests fail. And if your tests fail, then it means you didn't have a test that would cover that use case. So it's very kind of basic, and it's not really a fuzz testing tool, but it is an interesting look at how we could do stuff like that. There's another tool, and this is more newer. It's maintained, and it's still actively maintained. It's called Mutant, and it's basically inspired by Heckle, so it's the same thing. I would take a look at this tool and play with it and see if you like it. But we could really use like a real fuzz testing tool, something that works more similarly to other fuzz testing tools that are out there, something that takes user input, throws it through your code. So there's definitely room to improve there. There's a tool called Fuzzbert, written by Martin Bosslet. It's available there. I hadn't actually had a chance to play with it, so I'm not really sure like how well it works or if it works at all. But if you're interested in doing fuzz testing stuff, take a look at that, submit pull requests, play around with it. Yeah. As I mentioned, fuzz testing kind of gets a lot of papers written about it because it's security stuff, and security stuff usually gets a lot of papers on the subject. So a lot of resources about fuzz testing out there. So let's get mathematical. Let's get a little more technical, and let's go down into symbolic execution. So we talked about defect finding and fuzz testing and all that high-level stuff. Symbolic execution is interesting because it's a lot more. It's sort of this underlying thing that sort of guides a lot of these other tools. Basically what symbolic execution does is it runs your code with no immediate values. So you sort of have this algorithm that does math power, like 2 to the power of 8 or something. It will run it without actually using any of the numbers, and so we'll get this mathematical formula at the end. And that mathematical formula at the end is just basically a bunch of your code paths just like concatenated together, and then it just runs, it throws numbers and values into that mathematical equation, and it gets values out on the other end. It's similar to extended static checking, which I didn't talk about, the cool thing about symbolic execution is you don't need to tell your code what you're doing, we'll see what that means in a bit. But the other thing is you can tell which inputs generate what output, because I have this big mathematical formula, and I pass in a 2 here, and I get an 8 out there. I can control the input and output states. All right? I know what they are. So think automatic test case generation. I can automatically generate input values that will generate this output value that I know that I want to hit, or the other way around. So this is a bunch of C code that implements the power, although it's very convoluted, and I wouldn't recommend implementing math power this way. But just for example, you might have this complex code that implements some function. And if you read through this code, if you had a chance to read through it, you'll see that there is a potential bug there. If you kind of do math 2 to the power of 33, will index out of bounds on that array. So a symbolic execution engine can actually figure out that we're hitting an array out of bounds error, and using its magic and all this math theory stuff, it's able to actually generate a report for you saying, hey, if I pass 1 and 5 in, I get 1 out of this function. If I pass 2 and 8, I get 256. But if I try to pass 1 and 0, I get an array out of bounds error. And then if I try 1 and 33, I also get an array out of bounds error. And the way it picks numbers is sort of based on heuristics. It'll look at your array size, and it'll say, oh, 32, so I'm going to try 33, and I'm going to try -1 or something. So the symbolic execution engine is sort of based on a bunch of heuristics. But it's able to sort of intelligently figure out what values it needs to throw into a function. And so you can find these errors very quickly, and then we can generate test cases based on this automatically. So if my power function wants to accept or doesn't really, I could say like, hey, don't pass 33 in because my function doesn't accept that. I can also tell my symbolic execution engine, hey, don't try that number. And it can intelligently say, OK, fine, I won't try 33, I won't try -1, because those are the contracts. So what tools are out there for symbolic execution and stuff like that? If you use LLVM or LLVM-based languages, there's a symbolic execution engine called CLE, which can basically execute LLVM code and turn those into, like, symbolically execute that. If you're using JavaScript, there's a tool called Kudzu. I haven't tried Kudzu, so I don't really know how well it works, but you could do the same thing in JavaScript. And in Java and this other language called Spark, there's a tool called Kiesan, which is a symbolic execution engine for those languages. We don't have anything for Ruby in this space. I know this because I actually did my master's on this subject, and that's my master's there, where I wrote a proof of concept for symbolic execution in Ruby, but it's very basic, and I wouldn't recommend using it in any sense. But I mean, there is some work there, and it definitely needs more work. A lot of the reason that we don't have these kinds of low-level linting and static analysis tools is because Ruby doesn't really have a scientific community. And I think that's kind of a really sad thing for us to not really have the scientific community that Python has or other languages have, because we get things like those tools when we have a scientific community, when we have these people who are interested in those things. And it's really a chicken and egg problem, because we don't have the tools that are available for scientists, and then we sort of wonder why we don't have scientists that are using our language. So we really need to start developing these tools. So Brian Lyles is actually speaking today. He spoke about this at Wicked Good Ruby Conf, and he's actually giving a talk on scientific Ruby code, using Ruby code in scientific applications. And he's probably going to mention this Python versus Ruby thing. And basically, yeah, we definitely need more. We don't really have enough scientific tools in our community, and we could definitely use more. So I'm just going to sort of jump over what I talked about here. We are really good at testing, deployment tools, web frameworks. We have really awesome tools for those subjects. We have RSpec, we have mini tests, we have like literally hundreds of gems when it comes to testing. We do really good at those subjects, but we sort of get really focused on those subjects and we don't really do well on other subjects. So we're not very good at visualization, refactoring tools, profiling tools. We don't really have very many. And when we do, they don't really work well. So Ruby Debug 1.9, this Ruby Debug 1.9 gem that took 3 years after Ruby 1.9 came out to actually exist, is an example of that kind of thing that we're missing. We tend to attract web developers because we have the tools for web developers. We have good testing tools, we have good web frameworks, we have good deployment tools, so we attract web developers. Should we not try to attract a different set of developers to our language by developing tools for those people? Having a broader audience when you have a language is important. And it's important because when a broader audience comes to your language, they come in with a broader set of priorities. So someone who's doing science with Ruby is going to be much more interested in the performance of your interpreter than someone who's doing web development, doesn't really have a CPU bottleneck. And so if we had more of these, of the people in the scientific community, in the Ruby community, we would probably have a larger priority on improving performance of our interpreter. And then we might end up with a much faster interpreter in the end. So having this broader audience definitely improves the language in the end. We have to take responsibility of the fact that we don't have a scientific community. They're not here. It's not. We can't just say like, oh, why isn't the scientific community here? Why isn't the engineering community here? It's sort of our fault because we don't have the tools available for them. So I think it's important to actually say, like, if you actually are interested in this kind of thing, that you go out there and you do become a garbage collector and write these tools. The good thing is that there are great tool ideas just waiting to be implemented. There are literally tons of research papers in the fields that I mentioned. If you go trolling on scholar.google.com, and just type in some field that you're interested in, there are literally tons of papers on this stuff. I had a whole section on some of my favorite research papers in this talk, and I had to cut it out because there's not enough time. But if you want to talk about this stuff, you can come find me, and I can list off some titles of some really cool talks, some really cool papers. Reading papers might seem daunting if you've never done it before, and it was to me before I had. And once you read a couple and you sort of like ingest it slowly, it becomes much more natural, and it's really not as scary as it seems. So I would recommend not being scared by research papers. Some of them actually read very nicely. And with that, I want to thank you guys for letting me speak. If there are any questions, feel free to ask.